Hi, my name is James and I'm going to be talking to you today about developing for Azure SQL Data Warehouse. To start, I think it's best that we decide what SQL Data Warehouse is and when it's best to use it. Typically, we start with an analytical workload. That involves storing large volumes of data, consolidating data sets from across the enterprise or into a single location to perform some form of analysis. It's a place where we can shape, model, transform using set-based operations and aggregate data to get meaningful insights from the data. Okay? So we're going to be using a lot of ad hoc query analysis and basic SQL constructs to be able to perform that level of analysis. So the way I like to think about this is that this is SQL on SQL. Now there are some workloads that are not ideally suited to Azure SQL Data Warehouse, and it's important that we differentiate ourselves from those to make sure users do not accidentally use the wrong database at the wrong time. Many times, for example, in high-frequency workloads normally seen in operational systems or sometimes known as OLTP applications, those sorts of systems have very high-frequency reads and writes, very small inserts and very small selects, pinpoint lookups for customers and things like that. Those sort of systems and websites, etc., they're much better suited to something like Azure SQL Database. Similarly, streaming type of workloads where the data is coming in from, say, for example, an IoT scenario, that data is best landed and batched so that we're not trying to absorb a continual flow or stream into the warehouse. That has numerous benefits for the SQL warehouse architecture in terms of repeatability and restartability, but it is not. It helps the system work better for SQL. The other scenario that often comes up that people talk about is when to use Azure Data Lake Analytics with SQL Data Warehouse. And one of those scenarios is around what we call batch prep ETL. Some ETL operations are more row-by-row based procedural analytics. And this is where Azure Data Lake Analytics really comes into its own, given its procedural capabilities in batch mode. Okay? They're also very good for adopting and transforming data from, say, for example, JSON documents into a more tabular structure that is more directly suited to Azure SQL Data Warehouse. So let's have a quick look at the logical overview of SQL Data Warehouse. To start with, we have a distributed system that is based off of distributed storage. On top of that, we apply distributed compute. The compute can be scaled up and it can be scaled down on demand by the user, and that's something that we're going to look at in a moment. However, SQL Data Warehouse also enables you the opportunity to actually detach completely the compute as a pause operation and resume the compute by literally just restarting the warehouse. This enables you to have very fine-grained control over your compute consumption. Okay? Now, when it comes to distributed queries, this is something which gives SQL Data Warehouse its power and its ability to analyze massive volumes of data and to be able to achieve petabyte scale forms of analytics. Now, what it means is that when a user submits a query, that query is broken up and distributed across the compute and pushed down against the storage to process that result. As the results are calculated, the intermediate values are passed back through to the control node from the storage, and a user is then given the result. That means that there is multiple levels of calculation that take place, but it means that we're able to scale to reach new heights of capacity and management. Now, SQL Data Warehouse is a fully managed platform as a service. That means that you have all of the manageability of the system is governed by Azure. And therefore, the amount of time you need to spend focusing on that is greatly reduced. You only need to really think about how you design your system and to drive analysis from it. So it gives you a much more accelerated time, much more focused time. One of the nice aspects of being in the cloud is it enables different architectures that aren't necessarily available to you when you're in an on-premise environment. So in the on-premise world, you would maybe be somewhat constrained by your physical infrastructure and that might include your data centers. Well, with Azure SQL Data Warehouse, what we have is the ability to use geo-redundancy to actually maintain an even higher level of availability to maintain our RPO statistics. So you can see here that I have just taken a geo-redundant snapshot of our storage and I host that in another region's data center. So that if anything were to happen to the source region, we are able to reapply the compute and actually continue our business as usual. Now this is a developer session, and just want to call out the fact that from a range of connectivity, that can be from Windows or Linux, and we have customers that are running very happily on both platforms using a variety of these connection protocols. So in summary, SQL Data Warehouse is a scale-out query engine. Okay? It enables us to apply massive amounts of compute to distributed storage. Okay? Based on the decoupled nature of the compute and storage, that gives us that fully elastic up and down of compute layer, as well as a fully managed service through platform as a service. Now, by using the cloud, we're also able to have new and different disaster recovery options. So to place the rest of this talk into context, I think it's helpful to sometimes look at a very simplistic architecture diagram and then kind of drill into what we're going to look at. So here is a simple IoT scenario where we have an IoT hub on the left generating data and pushing that data through event hubs, stream analytics down to blob storage before Azure SQL Data Warehouse is used to ingest that data to perform some basic analysis. So for the rest of this talk, we're going to be really focusing on this middle section that involves the Azure SQL Data Warehouse, so we can understand how best to set ourselves up and create our tables to make the most of our solution. So the first thing we need to do is to be able to spin up our data warehouse service. So that is something that I'm going to just quickly demonstrate for you now, and for that we're going to skip over into code. So the first thing to note is that when you come into the Azure portal, you can come straight into the data warehouse experience and just hit the new button, hit data and storage, and there's the SQL Data Warehouse right there. This brings up what we call the provisioning blade, and we can start to add some details. So we could put build here, we can choose the amount of compute we wish to pay for. Okay, we can go up and down and choose something. We can apply a server. So the database is assigned to a logical server, and we can create one or we can add one in. And then we can also create as either a blank database, sample database, or actually even one of our backups we can reference in from here. We apply a resource group as a logical container of all the other aspects, and then we can basically hit create and go. Now that's how you do it through the provisioning portal, and many of you will have seen that before. So I'm instead going to do it something slightly different. We're going to look at this via T-SQL, because that also opens up the other option, which is to be able to reconfigure the max size of the database so we can control the total amount of storage spend as well. So we do need to have a database, a server to attach to, and as long as we can do that, we can go ahead and create the database straight away. So this query here is going to now go and create me a SQL Data Warehouse database, and you can see that the addition tells me that it will be of a data warehouse configuration, and the service objective tells me how much compute I'm going to apply, and then the max size, which is specified in gigabytes, tells me how big that database will be allowed to grow to as part of this configuration. Now that's going to take a little while, so the other thing I want to just go ahead and look at is a couple of the DMVs so that we can actually monitor this request. So let's just connect this one in as well. And we can see by querying here, we can see that we have an in-progress database build right here, and that session creation was specified. Okay, so we can see that that's running there quite happily. This DMV is called sys.dm operation status. So this will take a minute or two to come through. Now, once that has also been done, what we can also do is modify the database by using the alter database command to change our performance level from DW400, in this case, down to DW100. That's something that we can do using the DMV, the DDL command as well. So we're just waiting for the database to complete. Let's just double check that. And there you can see that the create database has in fact ended, and we can see the completed status there. So now what we can do if we wanted to is actually change the compute power by using this command here. So let's just do that. Now you'll notice that has come back straight away. The actual action is still going ahead. So in order to process it and make sure that we actually are able to connect, what we can do is we can instigate a loop around the operation status using a wait for command to be able to find when it is out of that completion status. We can then monitor it using this service objectives view, which is also pretty new. So that's just running now, and that should take about a minute. So let's go ahead and look at this service objectives view. If I run that now here, we can see that our databases are there, and we can see that the DW400 is still being specified against our build command, right? And that's because it's still in that state that we were looking at before. You can see the in progress command is running. So that loop is still waiting for the progress to complete. And as soon as it has, it will come back through, and we will see that our data warehouse has in fact resized. There you go. And on this side here, you can see that the data warehouse is now set at DW100. Okay, let's go back and have a look at how to design some tables. When we're designing tables, there are two types of distribution that we can use to spread the data around the data warehouse database. The first is the round-robin distribution, and the second is the hash distribution, and that's the optimized form. We're going to look at those with a demo in a moment. So here you can see that I've got some basic tables, and here is the build fact online sales table from Contoso. Now this table looks like just a regular SQL table. We have data types just as you would expect, and then down here is where the difference happens. We have this extra piece of information here that you wouldn't typically see on a SQL database. That database there, this command here, the distribution equals round robin, tells SQL Data Warehouse how you wish to distribute the data across that distributed storage. In this case, we've selected round robin. Round robin is essentially a random distribution designed to keep the data nice and even. Now we can optimize that distribution by using a technique called hash distribution. Okay, so here is the same table, notice the types, etc. But this time the distribution key has been chosen and we are going to hash over the product key. We will see if that's a good choice in a moment. Finally, I have one that is a third table here called the hash SKU, which is the same table again, but this time we've chosen the currency table. And we can again see if this is a good choice. So to come over here, this is our view that we're going to create. And this view very simply is designed to build out some analysis of the metadata to see how that data has been distributed across the storage locations. Now, this is quite a complicated view, and just so you know, this view is being posted up to azure.com, so you can just literally copy the code. I won't go through it in detail because it is quite involved piece of code, but it's very simple for you to be able to create that into a view, as I've done here, and then just execute it to get the information out yourself. So if we just look here, connect in to our data warehouse, we can then query the round robin table, and we can see by looking at the row count here that the random distribution has evenly distributed the rows across all of the disparate storage locations. Now, how do we then go and decide to optimize? Well, one of the things that we can do is we can profile our tables to look at different key options to decide which hash key we can use. So this is a simple little query here that we can use for profiling. And when we run this query, what we're doing is we're looking to see what the range of values are. As a general guide, you want something between at least sort of 600 to 800 distinct values, and you really want the values, the rows, to be evenly distributed across those values. If you have that scenario, then you're much more likely to get a nice even hash of the data. Here you can see that we have 2,516 values, but the range is from 304 rows per product all the way up to 273,000. So that might be a bit of a concern, and we would have to look at that, and we can do that by actually querying the metadata to see how the hash actually handled the problem. So we can run the same query again, and we can see whether the hash has indeed sorted the problem out. Now here we can see across our distributions that now the maximum is up here at 485,000, and down here we have a couple down at 94,000. So it's not perfect, but it might be good enough for us for the purposes of our analysis. However, there are scenarios where this can go wrong, and you need to understand how to look for that. So remember, we had that SKU table that we distributed by the currency column. Let's look at what's happened here. Now, in this scenario, what's happened is that there was actually only one value in the currency key. So what's happened is that all of the rows have been hashed into this one distribution. Now, the challenge here is that all of the compute is actually only attaching to one part of the storage to actually process the data. So that's not ideal. So we would not look to use the currency key as our distribution key. In this case, product is the far better choice. Now, you might want to consider something like the null distribution, right? So what happens if I have nulls in the column that I wish to use? That can also have the same effect. The problem with null is when it's hashed, it actually has the same result in that the data all ends up in the same one. So if your distribution key, say for example, we accepted null as our product key and accepted null, then we may find that we get a disproportionate number of values all being hashed into one distribution. So as a general piece of guidance, I would generally avoid a nullable column for my distribution, or be very careful to make sure that I have a very small number of nulls in that column. Now, There are a few other things that we can look at, and we do have to be kind of mindful of time. But one of the things that we have to be careful with is our data types. Okay, so for example here, this query here, if we were just to run this query here has our hash distribution by product, and the dim products here is also hash distributed. This is an ideal scenario because the distribution is based on the type, so we actually get a good join because the data is hashed into the same locations. So that's a good scenario here. Now, what that means is that when we do like query plan analysis, we'll actually see that we get fewer data movement operations as a result. Here you can see that we have 13. Now, by contrast, this table here, the product key, I have actually converted over to a big int. Now it's joining here to product on the product key, but this product key is an integer to a big int. Now because those types are different, the values, even though the values themselves are the same, product ID 1, product ID 1, the type is different, and so they actually map up differently. You can see here that the hash distribution count is higher as a result, right? The number of operations is higher because of that. Now, lastly, one of the things I want to show you here is that our table can also be impacted by the length of variable length columns. So here you can see I have a table, and this time I've converted all of the columns to varchar 500, save the product key. Now, the problem with this is that when data moves around the system, because it's a distributed system, those rows enter what we call buffers. Those buffers, fixed width as far as variable length columns are concerned, when they're under a certain threshold. That threshold is about 32 kilobytes. So what's going to happen here is that all of these varchar 500s, even if they only have a very small amount of data in them, will actually be exploded to the full 500 bytes. Now, how that implicates us is when we look at what we call the buffer density. And again, I have another view here which will be available on Azure.com at a later point. You can see here that our ordinary tables, there's products, that hash products table, that's got 125 rows in its buffer, versus here the 119 rows because of the big int. Now, this is our varchar table that we were just looking at. Can you see that there's only 3 rows in the buffer? And that's because the row has been expanded to its full width as it was moved into the buffer. So as a general piece of guidance, it's always a good idea to try and optimize the types to get them down to the reasonable levels and not just accept them for what they are. Okay? Now, so just returning back to the slides. So now we've finished with the demo for the table design. Let's now also consider one other key factor when we're thinking about tables. That is partitioning. And one of the things we need to think about with partitioning is that a distributed system is actually multiple storage locations. And that affects how we think about our partitioning of the data. Typically in a SQL Server database, you might partition the data by day purely because that's how you are processing the data, and you only really have one table. Under the hood of SQL Data Warehouse, you actually have many, many tables, and so the data is divided already before you even consider the partitioning. So here, let's look at 2 examples. One is a terabyte, and the other is a 50 terabyte table. So here, the distribution count that we have, i.e. the storage locations, is 60 in both cases. But the compression ratio that we might see on that table of that data might be around 5x. So if the data is unskewed, and the data has an even distribution across those nodes, then for the 1 terabyte table, if you divide that by the distribution count, we're going to get to roughly 3.3 gig per distribution. Now, if we then go ahead and partition that 3.3 gig is then going to be split into those partitions. Now, imagine that your data had been partitioned by month over 3 years. That's 36 partitions. So we would get down to this very small number here at the bottom, as opposed to the 50 terabyte table. Now, if we look at the 50 terabyte table, 166 gig per distribution, okay, if we now split that one by 36 partitions, we're now at 4.6 gig, a more meaningful and manageable size. So the takeaway here is that when you're migrating your data and thinking about how to partition, you really need to kind of think about A, the compression, and B, the compression rate, but also the fact that the data is distributed already, so that you can think about how big those partitions are, so to make sure that you are making sure that you're not over partitioning. Because coming from a regular SQL background, that can sometimes happen. So just to wrap up this section with some overarching guidance, the most important thing is to keep the column definition strongly typed. That's going to make sure that your buffer density is nice and high, and that your data is co-located when it comes to the distribution key. Now, the distribution key is read-only. So you want to make sure that that is a static value, i.e. you're not going to want to try and update that. And also aim for a not nullable column is my advice to you. Okay. Now, those columns that you use for the distribution key, make sure those are defined consistently. Sometimes in data warehouses, that typing over time has got a little out of hand, and so sometimes we need to bring that back into line when we're using SQL Data Warehouse to make sure that we get the best performance. Now, the hash and distribution can be optimized, and we have seen that can give us better performance and fewer movements in the system. Now, a good rule of thumb here for picking hash distribution columns is to look for the join and ideally the group by as well, because that will even help to eliminate movement completely. Finally, when you're partitioning, think about it as a data management exercise as opposed to purely a performance exercise. And consider the where clause in your SQL statements as being identifiers of specific columns that may be useful to you. And if you are looking at moving, say for an example, a SQL database over to a SQL Data Warehouse database, just bear in mind that you might want to increase reduce the granularity of that partitioning structure, i.e. from going from, say, day partitioning to, say, month as an example. So now let's look at how we load data into SQL Data Warehouse. And again, I think it's best that we drop to a demo because I think in that sense, seeing is believing. So if we come back into our environment here, and we open up our data loading query, the first thing we need to do is to actually set up and configure the data loading. And for that, we're going to be using Polybase. So the first thing we need to do is to create a master key and a database scope credential. This is what gives us our access into the storage containers. And then here is our external data source. This is going to tell us where the data is in blob storage. You can see here that we have both the storage account and the blob container, and we're mapping in the credential that gives us the permissions to go and access that data. Now, secondly, the data is largely tabular, but so we are going to use delimited text for this exercise, which is why we're going to use an external file format of type delimited text. But we're going to look at it in two forms. One is in an uncompressed state, and this is the external file format definition for that. And then the second one is the external file format which is compressed, using the data compression section right here at the end. Now, to actually map in and load data, the first thing we need to do is to create what we call an external table. It's called an external table because it doesn't actually contain any data and references data that lives outside of the database. So in this case, what we're going to do is we're going to create an external table called uncompressed1 of our fact sales. And you can see here that it's text file format, and we've mapped in the location, which is a specific file, and also the data storage and the text file. So we're going to load that, create that external link. When we create that external link, we're then able to process the data via a load. So let's just see that go through. So what it's doing here is it's just validating all of the credentials and creating the external table. And now we're going to use a piece of syntax called a CTAS to actually load the data. Here you can see that we're reading from the external table, and we're actually going to push that data straight into SQL Data Warehouse, okay, into a new table called CTAS uncompressed1. And I can run that here. So that is now running, and we're now loading data. And I can use these commands on this side to be able to analyze how we're actually processing that data. So I can use this DMV here, which is a combination of requests and DMS workers, to be able to see that our data is coming in. Now, the interesting thing here is that the data is running and it's coming in parallel, because we can see we've got 124 rows here. And over here, we can see that the data is flowing in across all of the distributions for both readers and writers. Now, this extra command here is the PDW DMS external work command. This command is showing us how the data is being read in parallel by Polybase. And here we can see that we're using something called a file split. And the file split, which is noticed here, is the read offsets of our input file. And you can see that there are 3. And that's because the data is in that single file. But we can improve the situation by using loading the same data. Notice that one took 1 minute and 8 seconds. Oh. This time we're going to load in the uncompressed data here using 60 files. That means the data, the same number of rows, is now been split across 60 files. Now look here at what's happened to our external work. Those file splits, we're now actually running across many, many more splits, because we're getting multiple splits, one for each file, because there's different offsets in the file. So now we would expect this to load in faster than the one before. And you can see that that query has taken only 27 seconds to run. So we've doubled our throughput on load just by using uncompressed and splitting the data into multiple files. Now what happens to that compressed data? Well, this time we need a different external table, because we're referencing the external table file format for the compressed data. Here you can now see that we actually only get one split, because all of the data has to come in from one side. One of the things that we learned when we're dealing with compressed data for delimited text is that compressed data, you basically can't have multiple readers reading the file. So we limit our parallelism somewhat. Okay, so this we would expect to take longer than any of the other options. So how do we mitigate for that? You see, we're already at 45 seconds. Now, how we mitigate for that is that we actually go back to the multiple file options. And basically what we need to do is to make sure we've got as many input files as we have readers. And I'll give you a table for that in a second. But here you can see that if I was to create this table here, I could create the table, the external table. So now we're going to try and just execute the compressed file load with just a single file, and what we will see when we actually look to monitor the load here is that the compressed file only generates a single split. And so because of that, that's going to impact our ability and our speed of load. Because delimited text, we can't have multiple threads all reading the same physical file, because the file has to be decompressed in order to be able to read it in the first place. And that affects the throughput at which we can ingest the data. Bear in mind that on the uncompressed, a single file was 1 minute and 8 seconds. This time, we expect that to take a bit longer, because we also don't have the ability to apply multiple readers to the problem. So let's just see how we could mitigate for that. Well, one of the things that we can do is to actually split the data again into multiple files. And by splitting the data into multiple files gives us the advantage of being able to apply single threads to each one of the files in the process. Again, that kind of gives us back our parallelism. Notice that took 1 minute and 23 seconds just to load that single compressed file. Notice we're using exactly the same data in every case. So now let's see what the difference is when we actually load that data for our 60 files and see how that does. Again, we can come back here and look at the external work DMV, and you can see that we again have our 60 splitters because we have 60 files. So now we're reading that data again in parallel, okay, which is great news for us because now we have multiple splits. Everyone's reading a different file, so that's again means that we're getting the parallelism and the throughput. And you can see that this is going to take longer than the uncompressed, because obviously we're having to go through the process of decompressing those files, but it will still finish faster than the single file uncompressed. So in terms of our speed, the 60 file option uncompressed was the fastest, then 60 files compressed, then single file uncompressed, and then single file compressed. And the difference was 27 seconds at the slowest, at the fastest, and 1 minute and 27 seconds at the slowest. So that's basically what I wanted to show you for our loading. And just to kind of give you an idea here about what we should be, where we should be thinking in our heads around loading compressed text, is that we really need to make sure we have at least one file for every reader. Now this is something where you might consider increasing the amount of scale that you have in your load so that you get more readers. Notice here at DW100 you have 8 readers, which means that you would need some kind of multiple of 8 on the file. But down here at DW1000 you have 60 readers, so you're able to have 60 files and each one of those files be read at the same time. One thing I do want to call out, this is only specifically relevant for delimited text. If the data is in ORC or Parquet file format, which we also support, those can be read in parallel because we can go after different blocks. It's just a different way that those file formats are compressed. Now, when we think about batching those loads and go back to our IoT scenario, one last thing to think about is really around the batch size. Now, trickle loads tend to have a very a high maybe potential number of incoming rows that are singleton inserts, and so batching those up makes a lot of sense for us because that's how we can apply the fastest parallelism. Now, if we take 3 examples here, one at 500 rows a second, one at 1,000 rows a second, one at 2,000 rows a second. Now, those 3 scenarios, we're going to look to load this data directly into a column store. Now, column stores have a threshold themselves, and that is that we need to have at least 102,400 rows per distribution in order to go straight to column store format, which gives us the cleanest, simplest ETL process. Now, if that's the case, if we have 60 distributions, that means that we need to have an input of 6.144 million rows in order to be able to get over that threshold, assuming we have an even distribution. So on that basis, you would need to, at 2,000 rows a second, you would need to kind of hold off your load till you got to about the hour mark before you would consider making a load of data. Now, we've shown you here how to use Polybase to do the data loads. You can also use Azure Data Factory, which coming very soon will be able to leverage Polybase under the hood to get very fast throughput. But you can also use integration services, BCP, and a host of other third-party tools, including the likes of Informatica. So, just like to close to give you some resources. I've shown you some interesting views to use. Those are being published on azure.com, so please go and make sure you take a look at those, as well as the other SQL Data Warehouse documentation. The Polybase Data Loading Guide is also available on there as well. And there are also going to be other SQL Data Warehouse related content, so please head back over to Channel 9 and check out some of the other excellent video footage there. Thanks very much for your time, and I look forward to seeing you at the next build.